Okay, Algebra 1, Lesson 3.2, we're talking about linear functions. So let's look at an example. We talked about function input and output last time we were together, so that's what we talked about, the concept of a function. So let's look at this exercise here. Think of a number, okay, multiply that number by 9, subtract your original number, and then divide that number by 4. So if I think about this, let's take the number 0. Multiply that by 9, I get 0. Subtract 0, and I get 9. Divide that by 4, and I get 9/4. The number 2, multiply that by 9, I get 18. Subtract 2, I get 16. Divide by 4, I get 4. Number 10, multiply that by 9, I get 90. Subtract 10, I get 80. Divide that by 4, I get 20. Negative 5, multiply that by 9, I get negative 45. Subtract 5, negative 5, multiply by 9, I get negative 45. Subtract negative 5, so negative 45 minus negative 5 becomes negative 40. Divide that by 4 and you get negative 10. Negative 6, multiply that by 9, you get negative 54. Minus negative 6, and that gives you negative 48. Divide that by 4, and you get negative 12. Think about with the value of x. You take x and you multiply it by 9, okay? Then you subtract x, and you divide all of that by 4. So this turns into what? 8x over 4. Did I do that right? 8x over 4, which is just 2x. And then I made a mistake here. This original number is 0. Multiply that 9, you get 0. Subtract 0, you get 0. Divide by 4, and you get 0. So a mistake on that guy. So this is the rule of what's happening with this particular example, okay? But what you see is algebraically, when you look at what they asked me to do, multiply by 9, subtract the original number, divide by 4, it's equivalent of doubling the number. So if I look at each of these, all I did was double the original number that you see there. So in the puzzle that we created above, we're used to graphing lines with the variables y and x. So for example, what we saw above was the input was x, and then the output was y equals 2x, okay? Another way to think of it, it was a rule for x. X was your input, and the output was 2x, okay? Now, all we can do is just, rather than using the y, we can just say, let's give that rule a name. Let's say it's f. So I can just say that f, pardon me, if I look at this, giving this rule a name, my input is x, and I can say my output is just f equals 2x. So what we see here is that f is a function. So f is a function of x. So if you give me an x, I will tell you what f is, okay? The f value depends on x. So rather than writing f equals 2x, we're going to write it a different way. This means that f is a function of x. Now you might think, okay, you're used to f times x. Well, this means something different. So we're going to say f of x, this is the way we say this, f of x equals 2x. So still your input is x, and your output is f of x. And then 2x is the rule of what you do with the x, okay? So this is a notation change that stays with you through all of math. You're accustomed to seeing y equal 2x, you plug in x to get y. We're going to switch that now and start saying, well, instead of saying y is equal to 2x, we're going to say f parentheses x, or f of x. So we're saying f is a rule, f is a function, it depends on x. So what this means is you substitute an x into this rule. So you substitute an x into 2x. So if you look at this, x is an element in your domain. That means it's your input. If you double it, that's what I'm doing. I'm doubling x. I get output. My output is my range. And then the notation we use for this is just f of x. Okay, so f of x is equal to 2x. So an example here is if I had the rule f of x equals 5x plus 1. What is the value of this when x is 3? I'm just asking you to plug in a 3. So you say that f of 3 is equal to 5 times 3 plus 1, which is 16. So what is the meaning of f of 3? It's the value of f when you plug in a 3. So the meaning of f of 3 is the output when x equals 3. For what value of x is f of x equal to 6? Okay, so I know that f of x equals 5x plus 1. Well, when f of x is equal to 6, then 6 equals 5x plus 1. Subtract 1 from both sides. 5 equals 5x, so x equals 1. Okay, so I can use it to solve for, like if I give you an x value, you can give me the f value. If I give you the f value, like 6, you can tell me what x makes that true. Evaluate these functions for x equal 4. So we're asking for f of 4. That is equal to negative 2 times 4 minus 3, which is negative 11. Over here, f of 4 is equal to minus 4 squared plus 1. That's negative 16 plus 1, negative 15. Evaluate these for f of negative 2. So f of negative 2 is equal to negative 2 minus 3, which is 4 minus 3, which is 1. Another way to think about it, when you're substituting in to a function, this is what the function f does. It takes a value, it squares it, it puts a negative in front, and adds 1. So if you're asking me to evaluate f of negative 2, then this is going to be negative 4 plus 1, which is negative 3. Now, how would I graph the function f of x equals 4x minus 2? Just think of it, you're used to thinking in terms of y. This is the same function as y equals 4x minus 2. So the f of x, really, it's your y value, okay? So this one, I know this has a y-intercept at negative 2. It has a slope of 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So this is the function, okay? So there's really nothing new here. I just use slope-intercept form to graph this function, okay? So f of x, this represents your y value. And then x represents your x value in function notation. So when I start talking about functions, you're used to thinking of equations, but I can look at data like this. The cost to make up 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? So first of all, if this is going to be a function, I need to determine the relationship. So what is the slope between these two lines? It's going to be 32 minus 17 over 2 minus 1. So this is what? 15. look at the slope from here to here. It's going to be 47 minus 32 over 1. That's 15. The slope from here to here is 62 minus 47 over 1, which is also 15. So the slope between all these points is the same. That's what it means to have a linear relationship, because you know when you look at a line, if you can determine the slope at any point on that line, you know the slope everywhere. So I can figure this out. This is a line that has a slope of 15, and I know it goes through the point 117. So if I look at this, this is going to be, if I look at y equals mx plus b, then I know that y is equal to 15x plus b. Substitute a 17 for y and a 1 for x, and that's when you get b is equal to 2. So this is y equals, 15x plus 2, but as a function, using function notation, I'm going to write f of x equals 15x plus 2. So what is the cost of 20 bracelets? So x is the number of bracelets, so f of 20 is what? 15 times 20 plus 2. So that is what? 300 plus through. So $302 for 20 bracelets. How many bracelets can you make for $152? So that's my y value. So if I look at this equation right here, I'm going to say 152 equals 15x plus 2. So subtract 2 from both sides. I'm going to get x equals 150 over 15, which is 10. So you can make 10 bracelets for $152. So again, really nothing new from a math standpoint. I just created a linear function. If I look at this one, write a linear function for this data. Okay, the slope is going to be, if I look at these 2 points, 4 minus 1 over 2 minus 1, which is 3. And then the slope is 3 at all different points. So I know that this is y equals mx plus b. You can even write it this way, f of x equals mx plus b. So f of x equals 3x plus b, and then pick a point, 1, 1. When the y value is 1, the x value is 1. So b is equal to negative 2. So this function is f of x equals 3x minus 2. Let's look at this one. Is there a constant rate of change? Rate of change is just slope. So if I look at these first 2 points, the rate of change is going to be what? 5 minus 3 over negative 2 minus negative 1. So this is 2 over negative 1 or negative 2. Look at these 2 points. The slope is going to be 3 minus 1 over negative 1 minus 0. So that is 2 over negative 1 or negative 2. Look at the last 2 points. 1 minus negative 1 over 0 minus 1 is 2 over negative 1, which is negative 2. Is there a constant rate of change? Yes, m equals -2. So write the linear function f of x equals -2x plus b. Now this one, I already know b, because when x is 0, if this goes through the point 0, 1, that's a y-intercept. If you didn't catch it, just 1 equals -2, 0 plus b, you're going to get b equals 1. So this is f of x equals -2x plus 1. And that's trivial to graph. Go to 1, then the slope is 2. Why do we use this function notation? Okay, you've been very comfortable using x's and y's, and now we switch it up to you. Leonhard Euler, great Swiss mathematician, was the first person to use this in the 1700s. Okay. Anyway, it's real helpful because later in math you're going to get more complicated functions, and so when you see functions that are more complicated, I'm going to do things like add functions together or divide functions or substitute one function into the other. So it's just much more convenient to switch gears and using function notation. So again, you've been used to graphing y equals, 2x plus 3, thinking of x and y's, okay? Now just think of it, it's the same thing. F of x equals 2x plus 3. F of 3 is equal to 9. So the x represents your x value, the f represents your y value in a function. Look at this example. Tamika records the outside temperature at 6 a.m. as -3 degrees Fahrenheit. The outside temperature will rise 2 degrees Fahrenheit every hour for the next 6 hours. If that increase in temperature continues, what will the temperature be at 2 p.m.? Okay. Now in this example, the independent variable is just going to be time. Time is going to march on regardless of what I do, but the temperature is what I'm measuring. So my independent variable here, or my horizontal axis, should be time in hours. And my dependent variable should be my temperature in degrees Fahrenheit. Sometimes it's better to define the time on the axis instead of using 6 o'clock, 7 o'clock, 8 o'clock. Just start with the origin and have something like time since. So it's better to say in this example, I'm going to let x equal time in hours after 6 a.m. So that way I can label this as a 0, okay? And then this would be 5, 10, 15, okay? So if I look at this, I know that the temperature at 6 a.m. was -3, okay? So I'm going to need to do some negative numbers on here. So let's just say, for example, if this was, say, -5, and this would be 0, and then this would be 5, and 10, and 15, okay? So they tell me that the temperature at 0 is at -3, which is right there, okay? And then I know it increases 2 degrees every hour. So every hour it goes up 2 degrees. Now I'm interested in what happens at 2 p.m. So that's going to be 8 hours after 6. So I just need to continue my graph. So that's at 6, 7, and right there is at 8 hours. Okay. So if we look at what function this might be, okay, I can see that this looks like a linear function. It's increasing by 2, every hour. I can do better than that. So let me try to draw a better line. and probably just use some of my features here. So insert. A line, so straighter line to have a better graph. There I go. Okay. So if I want to write the function here, this is just going to be f of x equals, what is it, 2x, and then it starts at minus 3, so 2x minus 3. And then I know what the graph looks like. I just sketched it there. Find the temperature at 2 p.m. So f of x equals 2x minus 3. So at 2 p.m., that is 8 hours after 6. So f of 8 is going to be 2 times 8 minus 3. 60 minus 3 is 13. So the temperature should be 13 degrees. If I look at my graph, 11, 12, 13, right there. Okay, 8, 13. So this was 13 degrees Fahrenheit. When will the temperature be 21 degrees? So this is setting my y value to 21. So f of x equals 2x minus 3. 21 equals 2x minus 3. 24 equals 2x. So x is equal to 12. So 12 hours after 6 a.m. is going to be at what? 6 p.m. is where I get that temperature. Okay? And that should lead us up into the homework for this section.